Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it.
This is 8.2, which is integration by parts. Right? And before we start this, let's recall something. And we're going to recall the product rule. And I'm going to do it in the differential version, which says v of u times v is u prime v plus v prime u. And if I rewrite this as more differentials, I have that d of u times v is v du plus u dv. Now, what I want to do here is I'm going to manipulate this expression, right? If I integrate everything here, what I end up with, the integral of a derivative, well, that's just uv, right? Because they cancel each other out. That's going to be equal to the integral of v du plus the integral of u dv. So what I want to do here is I'm going to solve for this integral over here. All right. So what I have there really is the integral of u dv is uv minus integral of v du. And that last line is integration by parts. So notice that integration by parts is essentially based out of the product rule, right? So we're going to be using this a lot when we've got products inside of an integral, all right? So that is integration by parts. So that is a formula. So I'll just formalize it by saying the theorem for integration by parts. And this is what it says. Let u and v be functions of x with continuous derivatives. Then the integral of u dv is uv minus integral of v du. Alright, so that is again what integration by parts says. So first let's start with a quick example. And here we're going to start with the integral of x e to the x dx. Alright. Now in here, I'm going to start by splitting this up in this manner. I've got a product of these two things. The first part is going to be our u, the second part is going to be our dv. So u is going to be just x, and dv is going to be e to the x dx. What we want from this part from u, we want to figure out what du is, so that would just be dx. On this other side, however, we want to figure out what v is, so it will be the integral of this. The integral of e to the x dx is just e to the x. So now we can go ahead and use our integration by parts formula. What we're going to say here is that this integral is equal to uv, so x e to the x, minus the integral of v du. And the integral of e to the x dx is just e to the x. So there you go. That would be the final answer. And if you really wanted to, you can factor out that e to the x, right? And we would have e to the x times x minus 1 plus c. But you don't have to. All right, you could have stopped at this line. All right. So before we do more examples, um, let's talk about how to figure out what u should be. All right, because if we had done this the other way, if we had let u be e to the x and dv be x dx, then this would not have worked. So let's discuss this question. The question here is, what should u be? All right. what should u be? And that question is really answered by this acronym. And the acronym is LIATE, LIATE. What this stands for is logarithmic functions, inverse trig, algebraic functions, trigonometric functions, and exponential functions. And it should be in that order, all right? So if you have a logarithmic function, that should probably be your u. If you don't have a logarithmic, but you have an inverse function, an inverse trig, then that should probably be your u. Similarly, if you don't have a logarithmic or an inverse trig, but you do have an algebraic, that should probably be the u. So on and so forth. Now, is this foolproof? No. There are definitely scenarios where you don't follow this. But for the most part, 90, I would say probably 90 to 95% of the integration by parts problems that you'll do, they will be following this acronym or this rule. So let's go ahead and do another example. Oh, excuse me. So now the integral of x squared times ln of x dx. All right. So in here, I see that I definitely have a logarithmic function, right? And from LIATE, well, logarithmic was the very first one. So I'm going to let u be equal to ln of x. dv, excuse me, would be the rest, which is x squared dx. So if u is ln of x, then du would be 1 over x dx. And if dv is x squared dx, well, then v would be x cubed over 3. At this point, we can go ahead and start applying the integration by parts. So this integral is going to be uv, so I'll write that as x cubed over 3 times ln of x, that's uv, minus integral of v du. And I can really rewrite this as x cubed over 3 times ln of x minus 1/3 times the integral of x squared dx. All right. And then to find that integral is pretty simple. So we have x cubed over 3 times ln of x minus 1/3 times x cubed over 3 plus c, right? And finally, as my final answer, I'll write this as x cubed over 3 times ln of x minus x cubed over 9 plus c, right? And we'll leave that as our final answer. All right, so that was example B. Example C. So example C says the integral of ln of x dx. Now, in this one, as written, it might not look like it's an integration by parts problem, but it is, all right? You might be thinking that this integral is very simple and that the answer is 1 over x. No, that would be the derivative. The derivative of ln of x is 1 over x, not the integral. It is very common to make that mistake. All right, so don't make that mistake. In here, what we're going to do is, well, we're going to follow that rule of LIATE. We're going to let our u be the logarithmic function, so just ln of x. And we're going to let dv be everything else. Well, what's everything else? Just dx. And if u is ln of x, then du would be 1 over x dx. And if dv is dx, well, then v would just be x. And now we're going to say, well, we can actually start applying the integration by parts rule. So we have that integral being equal to uv, so x ln of x, minus integral of v du, so x times 1 over x dx. Now this really just gets simplified to be x ln of x minus integral of 1 dx, right? Because this x times 1 over x reduces to just 1. So my final answer here would be x ln of x minus x plus c, because, well, the integral of 1 dx is just x. All right, and again, this was an example where it didn't look like it would need integration by parts because we don't have the product of two different functions in the integrand, right? So let's do another one. So that was C. Let's look at example D. And here I have the integral of arcsine of x dx. All right. And again, it doesn't look like it would be integration by parts because it's not a product. All right. But we already know from the previous example that it's possible to use integration by parts even though I don't have a product. So I want to start with, well, what should u be? All right. Well, if you recall from LIATE, it was LIATE. The I stood for inverse trig, and we have inverse trig here. So I'm going to make that our u, arcsine of x. And then dv would be everything else. So in this case, it's just dx. And solving for du, I end up with 1 over the square root of 1 minus x squared dx. Solving for v here, I end up with just x. And now I can go ahead and use the integration by parts formula. So we're gonna say now that we have uv, so x arcsine of x minus integral of v x du. So 1 over the square root of 1 minus x squared dx, right? And at this point, I'm gonna say, well, let's rewrite that integral. Because in this integral, well, first let's rewrite it. So I have x arcsine of x minus the integral of x over, and I write it as 1 minus x squared to the 1/2 dx. Now in that integral, I'm going to do a u substitution, all right? So let's see what happens. But I can't use u because I already technically used u up here. So I'm going to use a different variable. Instead of u or v, I'll use t. So I'm going to make a t substitution. And I'm going to let t be equal to 1 minus x squared. So therefore dt would just be negative 2x dx. All right, and that's just, we're just tackling this integral right here, right? So that integral now becomes, well, it'll be the integral of, instead of this x up here, well, we didn't use it for anything, so it's still there. We didn't use it for our substitution. On the bottom, 1 minus x squared to the 1/2. That 1 minus x squared was our t. So I have t to the 1/2 dx. Well, from here, dx is just dt over negative 2x. So I have dt over negative 2x. You notice there that the x's reduce. They go away. And this just becomes, this integral becomes negative 1/2 times the integral. So hold on. Let me rewrite this in yellow. Negative 1/2 times the integral of t to the negative 1/2 dt, right? All I did there was rewrite the t to the 1/2 with a negative exponent on the numerator. And at that point, we see, well, that integral just becomes negative 1/2 times, add 1 to the exponent, divide by the new exponent, which is multiplied by its reciprocal, and then plus c. So what we really get here is negative t to the 1/2 plus c. Notice that the 2 and the 1/2 reduce. They cancel each other out. But that was just this integral, right? What I circled in yellow. We still have everything else here on the outside. So my final thing that I can say here is that this is x times arcsine of x minus this integral. But this integral we found to be negative t to the 1/2 plus c. So in here, well, the problem here should not be about t. Oh, look at that. I should have done that before. I should have rewritten this as the negative of, well, t was 1 minus x squared. So 1 minus x squared to the 1/2 plus c. There we go. So that's what I'll write over here. We had minus negative of 1 minus x squared to the 1/2 plus c. And then minus a negative is a positive. So I have as my final answer here, x arc sine of x plus 1 minus x squared to the 1/2 plus c. And that would be the final answer there. So there we just saw two examples where it didn't look like it was integration by parts, but it was. Let's do another one. So that was D. E. All right, so in here, E is the integral of x squared times cosine of x dx. All right, so now in this one, the very first thing I need to do is recall what the acronym was. And the acronym, remember, was LIATE. So logarithmic, no, we don't have that. Inverse trig, no, we don't have that. Algebraic, we do have that. Algebraic are things like polynomials, things that have just x's on them. Think of like what you did in your algebra courses. All right. So we do have an algebraic. So that algebraic function is going to be our u. So let's make u be our algebraic function, which was x squared. So therefore, dv would be the rest. So it would be cosine of x dx. So if u is equal to x squared, then du is equal to 2x dx. And if dv is equal to cosine, well, the integral of cosine is sine. So now we can go ahead and say that this integral becomes, well, uv, so x squared times sine x, minus integral of v du. I'll write that as 2x sine x dx. And look at that. We have another integral that looks kind of similar in the sense of we have an algebraic times a trigonometric. So in there, we're going to do another integration by parts, right? And we're going to do it just for this integral. So let's look at just that integral on its own. So we have the integral of 2x sine x dx. And in here, I'm going to let u be the algebraic part, which is just 2x. And dv is going to be the trigonometric part, which is sine of x dx. Now, if u is equal to 2x, then du is equal to 2 dx. And if dv is equal to sine, well, the integral of sine is negative cosine. So now we can see that this integral really becomes uv, so negative 2x times cosine x minus integral of v, negative cosine x, du, 2 dx. So rewriting that is really just negative 2x cosine of x plus 2 times the integral of cosine of x dx, right? And that's an x in the middle. And at that point, we would say, well, the integral of cosine x, we know what that is. That's just sine. So we have negative 2x cosine x plus 2 sine of x plus c. But that was just that integral. So what we really have here, and I'll start writing it white again, what we really have here is x squared times sine of x, let's scroll up, x squared times sine of x minus, because it was minus the integral. And the integral became this thing down here, negative 2x cosine of x plus 2 sine of x plus c. Distributing this negative sign, I end up with x squared sine of x plus 2x cosine x plus, it's not plus anymore, minus, we're distributing the negative, minus 2 sine x plus c. All right, and that would be the end of that. Notice what happened in this problem. We had to do integration by parts twice, right? Once up here, where I had the x squared with the cosine x, and I did integration by parts for that integral. But then we have to do it again for this integral, right? That is something that is very common with integration by parts, all right? You might have to do integration by parts and then again integration by parts to continue to do the problem. And we only did it twice because over here, by the time we got to this step, it was no longer required to do integration by parts, right? But again, in here, we had to do integration by parts twice. All right, so that was example E, I believe, right? Yeah, E. So F. And this is what F says. That's an F. And F says the integral of e to the negative 3x times sine of 5x dx. All right. Actually, you know what? I'm going to do a simpler version of this first, and then we'll tackle this problem. Let's start with just that. I'll just rewrite it. We'll start with just e to the x times sine of x dx. All right, we'll start simple. Then we'll tackle that other one, that other version. I'll think about it. I don't know. But now, let's do this. So here, from LIATE, so remember that's logarithmic, inverse trig, algebraic, trigonometric, and then exponential. Trigonometric came first. So what we can do here is we can say let u be equal to sine of x. Therefore, dv would be e to the x dx. So if u is sine of x, then du would be cosine of x dx. And if dv is e to the x, well, v would be just e to the x as well. So what we get now by applying the integration by parts, I have uv, so I write it as e to the x sine x, minus integral of v du, so e to the x cosine x dx. And now in there, I'm going to have to do integration by parts again. So in here, I'm going to say, well, let u be equal to cosine of x. Therefore, du would be negative sine x. And then dv would be e to the x dx. Therefore, v is just, again, e to the x. So applying that, what do we get? So this first part remains unchanged. E to the x times sine of x minus. Now this integral becomes uv, so e to the x cosine x, minus integral of v e to the x du. So that's, oh, I missed the dx there. Look at that. Dx. All right, cool. So negative sine of x dx. And distributing this negative, what we really have here is e to the x times sine of x minus e to the x times cosine of x plus the integral, well, not really plus, because minus times a minus times a minus becomes a negative. So it's going to be minus here. Minus the integral of e to the x sine x dx. But before I continue here, let's look at what we found. Our original integral was this. As we went through the problem, look at that. We have that same integral again. So if we were to continue to apply integration by parts, well, we would never finish, all right? Because in here, what we essentially have is um, two functions that are going to be repeating in their derivatives. Now, this next term I'm about to say, it's not an official term, but I like to call these cyclical functions. No, what? I said it wrong. I like to call these functions with cyclical derivatives. All right? And by that I mean that if you take enough derivatives, you end up back at what you started. So for example, or at least something similar to what you started with. So if I had sine, right? After four derivatives, I'm back to sine, right? Because it's sine then cosine, right? It's sine then cosine then negative sine, negative cosine. So enough derivatives, I'm back to sine. That same thing happens with cosine, right? That similar idea happens with e to the x. Right away, you're back at e to the x. So what are we going to do here? Well, let's look at this. Essentially, what I've got here is an equation that says something similar to a is equal to b minus c minus a. And what I want to do here is I want to solve for a. So I need to bring all the a's to the same side. So I have 2a is equal to b minus c, which would tell me that a is equal to 1/2 times b minus c. So that is the same exact idea that we're about to apply here. We have our a and our a on opposite sides of the equal sign, right? So what we can do here is bring everything to the same side. So I'm going to rewrite this now as 2 integral of e to the x times sine of x dx, and we're going to let that be equal to, well, we already found that it was equal to e to the x sine x minus e to the x cosine x, and then plus c. Don't forget about your constant of integration. So in here, now if I divide both sides by 2, I can confidently say that the integral of e to the x sine x dx would be 1/2, well, let's factor out the e to the x. If I factor out the e to the x, I end up with e to the x over 2 times sine of x minus cosine x plus c. All right, and that would be the final answer there. All right, now I do want to mention something here. We would have still gotten the same answer if I had started with u being e to the x and dv being equal to sine of x dx. I will let you guys do that as an exercise on your own so that you can see that it gets the same exact solution. All right, because when we have these two, this kind of integral where again they've got cyclical derivatives, and again that's not an official term, that's just my own personal term. Where they got cyclical derivatives, it doesn't really matter which one u is and which one dv is. So now let's do a harder version of this same kind of problem. All right, the one that I started to write before. So g. And g says the integral of e to the negative 3x times sine of 5x dx. All right. Now, just to follow the norm of LIATE, I'm going to go ahead and continue to use the trig stuff for my u. But again, we would get the same exact solution if I did the exponential stuff for the u instead. So in here, I'm going to say, well, u is going to be the trig stuff. So sine of 5x dx. Well, no, not dx, just sine of 5x. Well, that's a 5. And dv is the rest of it. So e to the negative 3x dx. And if u is sine of x, then du is 5 sine of, excuse me, 5 cosine of 5x dx. And v would be, well, the integral of e to the u is e to the u, so e to the negative 3x, but over negative 3. And then downward dx, all right? At that point, we can say that this integral, well, we can apply the integration by parts. So uv, so I'm going to write that as negative e to the negative 3x over 3 times sine of 5x. So uv minus integral of v, negative e to the negative 3x over 3 times du, 5 cosine of 5x dx. So I'm going to rewrite this now, factoring out that negative as well as the 5/3. So I have negative e to the negative 3x over 3 times sine of x plus 5/3 times the integral of e to the negative 3x times cosine of 5x dx. And what you'll note there is that I once again need to do integration by parts. So what I'm going to do here is I'm going to say, well, let u be equal to cosine of 5x, right? And I'm forced to make that be the u because I started with u being the trig stuff at the very beginning. So we need to be consistent and continue to let u be the trig stuff. So then dv would be the rest, which is just e to the negative 3x dx. So therefore du would be negative 5 sine of 5x dx, right? Because the derivative of cosine is negative sine. And then by the chain rule, that's where I get that extra 5. And v would be e to the negative 3x over negative 3. All right, just like before. So now, what does that give us now? Well, that gives us the following. So we can say now, well, this first part's still there. Negative e to the negative 3x over 3 times sine of, ooh, look at that. That's a bad copying error. That should have been 5x. All right, sine of 5x plus 5/3 times. We're going to use the integration by parts with this integral, but I'm leaving the 5/3 on the outside. All right, so uv, so I have e to the negative 3x over negative 3 times cosine of 5x minus integral of v du. So I've got e to the negative 3x over negative 3 times negative 5 sine of 5x dx. All right, that's a 5. So at that point, let's simplify this a little bit. So we've got negative e to the negative 3x over 3 times sine of 5x. Distribute this 5/3. So 5/3 times negative 1/3 is negative 5/9 times e to the negative 3x cosine x. Over here, how many negatives do I have? 1, 2, 3. So I've got 3 negatives, so overall it stays negative. So minus, and I'm distributing that 5/3. So minus 5/3 times the integral of, well, I gotta take out another 5/3 there. So that really is not 5/3, that's 25/9. All right. And again, that's because I'm taking this 5/3, distributing over here, and I'm taking these 5/3 and also putting them over here. All right, so 5/3 times 5/3 is 25/9. And what are we left with inside here? It's e to the negative 3x times sine of 5x dx. And look at that. I've got that integral again, e to the negative 3x sine of 5x dx. So we're not going to just go ahead and continue to do integration by parts because, well, we just found out that that's going to just repeat the cycle over and over. But what we can do is we can move over that integral to the same side. All right, and notice that I've got that negative 25/9. So I need to add that negative 25/9 to the left side. All right, so in here, essentially what I've got is a is equal to b plus c minus 25/9 a. And if I move this to the left side, I end up with, well, 34/9 a with equals blah blah blah, the rest of it, right? But that's the idea. And we're gonna move that piece over. So when we do that, so what do we have? So we have 34/9 times the integral of e to the negative 3x times sine of 5x dx. All right, that integral is going to be equal to what we had left over here. So that's negative e to the negative 3x over 3 times sine of 5x minus 5/9 e to the negative 3x cosine x plus c. Don't forget to put your constant of integration. So our final answer here, well, I need to multiply both sides by 9/34 because I need just the integral by itself. So the integral of e to the negative 3x times sine of 5x dx is going to be this entire stuff multiplied by 9/34. So 9/34 times, I'm just going to go ahead and copy and paste this. Look at that. Technology is amazing. Anyway, so I've got an extra negative sign over here. I don't know what that was. But anyway, so that's what we end up with there. Now, distributing this 9/34 here, um, what we end up with here ends up being uh, negative 3 e to the negative 3x sine of 5x over 34 minus 5 e to the negative 3x cosine. This cosine x should have been cosine of 5x. It should have been cosine of 5x. Look at that. I copied that wrong here. Ah, man, that same mistake happened earlier. So this is 5x. If you caught it while listening to me, good. Good job, you. Let me fix it though. So here, oh well, didn't erase that. That should be a 5x. Similarly over here with both of these. So that should be a 5x. Alright, and all of this over, well, these lines cancel each other out, so it's just 34 plus c. Alright, and that would be the result there. Alright, so that was example G, I believe. Now let's talk real quick about something called tabular integration. I want to do just one quick example before we do some harder examples of other stuff. So tabular integration. All right. So this only happens in very specific kinds of cases, right? I think I'm example H. So this is one of those cases. And in here, I'm going to go ahead and say that this example is the integral of x to the fifth times sine of 2x dx. All right. Now, this method that we're about to do, it only works in very specific scenarios. The scenarios where it works with is where we've got a function that has a terminating derivative. Again, that is not one of those real words. That's a word that I made up. And by that I mean, by terminating derivative, what I mean is that if I take enough derivatives, the function goes away, right? And in here, if I take enough derivatives of this, I'm going to end up at 0. Compare that to this part over here, sine. If I take enough derivatives, well, it's never going to go away. You just end up back at some form of sine or cosine, right? But with x to the fifth, if I take enough derivatives, it goes away. So this tabular integration only happens when you have that scenario, right? It only works when you have that scenario where one part definitely goes away. So what we're going to do here is we're going to set up a table, all right? And the table is as follows. We're going to say we're going to have a column for U and a column for dV. And we're going to start by taking derivatives. So we're going to start with x to the fifth, take the derivative, 5x to the fourth, take the derivative, 20x to the third. And we're going to do that until we have no more derivatives to take. All right. So there we go. So this, again, is an example of a terminating derivative in the sense of if I take enough derivatives, it goes away. And if that's our u, then our dv is the rest of it, which is sine of 2x. And over here, we're going to be just taking integrals. The integral of sine of 2x is negative cosine of 2x over 2. The integral of negative cosine of 2x over 2, let's just keep this little chart handy. The integral of negative cosine is negative sine. So negative sine of 2x, but now it's over 4. All right. And that's from the u substitution that you will be doing. The integral of negative sine is cosine. So I end up with cosine of 2x over 8. The integral of cosine is sine. So I end up with sine of 2x over 16. The integral of sine of 2x is negative cosine of 2x. This is over 32. And finally, I'm going to do this until we're, sorry about that. I'm not sure what happened there. All right, so I'm going to do this until this, I end up with the same column here, the same row, I mean. So the integral of negative cosine is negative sine. So I have negative sine of 2x, but now over 64. All right. So now, the next thing we're going to do is we're going to start writing these symbols. Plus, minus, plus, minus, plus, minus, plus. All right. And in there, I started with a plus. We always start with plus, all right? And then we alternate them. We always start with plus and then we alternate them. The next thing we're going to do is we're gonna ignore the first dv as well as the last u. All right, we're gonna ignore every single one of those. And after that, what we're gonna do is we're gonna multiply diagonally. All right, so we're gonna multiply these two together, and then these two together, and then these two together, and so on and so forth. And now we're almost done here. The answer of that integral, all right, is going to be as follows. So perhaps I'll rewrite the integral. The integral of x to the fifth times sine of 2x dx. All right, and here we go. I want to multiply those first two, but notice I have a negative. This positive up here stays positive, so these two multiply by a positive, so I end up with negative x to the fifth times cosine of 2x over 2. Repeat, multiply these two, but make sure you apply this minus. So minus a negative becomes a positive. So plus 5x to the fourth times sine of 2x over 4. Multiply again, but now we have a plus sign. Plus 20x cubed times cosine of 2x, all of this over 8, right? And now minus the product of these two. So minus 60x squared times sine of 2x over 16. Right, that was these two. Plus the product of these two, but plus a negative is going to be a minus. So minus 120x cosine of 2x over 32. That was these two. Right? And then minus times a negative is positive, so plus 120 sine of 2x over 64, and then all of that plus c. If we really wanted to, we can reduce some of these fractions, right? This 20 and this 8, they're both divisible by 5, not by 5, by 4. So I end up with 5 and 4 down here. This 60 and 16, they're both divisible by 4. 60 divided by 4 is 15. 16 divided by 4 is 4. 120 and 32 are both divisible by 8. So I end up with 15 quarters again. And then 120 and 64 are again both divisible by 8. So I end up with 15 over 8. All right. I won't rewrite that, but that is the final answer. Now notice how much quicker this was than having to do integration by parts over and over and over again. All right. Each each diagonal line here essentially represents how many times we will need to do the integration by parts. And look at that. How many diagonals do we have? 1, 2, 3, 4, 5, 6. So we would have needed to do integration by parts 6 times for this problem. But because we know the tabular method now, it just becomes very simple. And again, one column just take a bunch of derivatives. The other column takes a bunch of integrals. All right, and that's how we end up with our final answer. Let's do another one. So that was H. So I. All right. I. And I says the following. I've got the integral of x to the 23rd times e to the x to the 8th dx. Right? That's e to the x to the 8th. All right. So in this one, the very first thing we're going to do here is let's do a substitution. We're going to do a u substitution. All right? Because I don't like this exponent of an exponent thing here. Right? So that's the very first thing that we're going to do, get rid of. So I'm going to say, for example, let t be equal to x to the 8th. Therefore, dt would be, well, 8x to the 7th dx, right? And at that point, that really tells us that dx is just dt over 8x to the 7th. So now, this integral now, what does it become? Well, it becomes, well, this x to the 23rd, we did nothing with that, so it's still there. This x to the 8th, that was our t, so I have e to the t. This dx becomes dt over 8x to the 7th. Next thing I'm going to do here is reduce the x's. So 23 minus 7 is 16. So I have 1/8 times the integral of x to the 16th times e to the t dt. The next thing I notice here is that x to the 16th, well, that looks very similar to t squared. And by that I mean it is just t squared, right? Because if t is equal to x to the 8th, then t squared is equal to x to the 16th. So we can rewrite this integral now as 1/8 integral of t squared e to the t dt. All right, and that is now an integration by parts problem. All right, as it was written originally, it would not have been an integration by parts problem, and the reason for that is because we have that e to the x to the 8th. All right, so what we did was we manipulated a little bit. So now in here, I'm going to apply that tabular integration uh, method. So I'm going to say we have a column for u and a column for dv. And in the column for u, I have t squared to t to 0. Cool. For dv, I've got e to the t, e to the t, e to the t, e to the t. Because all I'm doing there is taking integrals, right? But the integral of e to the t is just e to the t. Next thing I'm going to do is alternative plus or minus. Ignore the first dv and the last u, and then multiply diagonally. So what we're going to have now, and don't forget our 1/8 on the outside over here, we're going to have now a 1/8 times t squared times e to the t minus 2t times e to the t plus 2e to the t, and all of that plus c. Now, I noticed there that everything has an e to the t, so I'm going to factor that out. So what I have here is just e to the t over 8 times t squared minus 2t plus 2 plus c. But the problem was not about t, right? The problem was about x to the 8th. So we had to make sure that we keep it back into terms of x. So what we need to do here is replace every single t. So this is going to become now e to the x to the 8th over 8 times x to the 8th squared, which is x to the 16th, minus 2 times x to the 8th plus 2, and all of that plus c. All right. And that would be the final answer. But again, here, notice that we started by doing a simple t substitution, essentially a u substitution, but I didn't want to use u. And we went and did tabular integration. Now, let's do a couple of more. So that was example I. So J. And here I've got the integral of ln of x squared dx. All right. So look at that. It doesn't really look like it's integration by parts. All right. But it is. It is definitely integration by parts. So let's look at what to do here. Now I'm going to start this off in the same way that we started off the one where I just did ln of x by itself. Now it's just ln of x squared. And what I'm going to do here is I'm going to say let u be equal to our logarithmic part, right? The entire logarithmic part. So in here, we're going to say this is ln of x squared. And then our dv is just going to be the rest of it, which is dx, right? Now, at that point, what we need to do is figure out what du is. So we're going to find du, and that's going to be 2 times ln of x times 1 over x dx. And v would just be x, all right? Now, at that point, well, we're going to do our integration by parts. So we're going to say we've got uv, so I'm going to write this x times ln of x squared minus integral of v du. So I've got x times 2 ln of x over x dx. And at that point, well, we've got the x's canceling each other out inside of that integral. And we can rewrite this integral or this line as x times ln of x squared minus 2 times the integral of ln of x dx. All right, now in here, we've got another ln of x, the integral of ln of x. Well, let's see what happens there. Well, we actually did that. That was, I believe, the second problem that we did in here. So I'm going to scroll up real quick to show you. Where is it? Third problem. There we go. So the integral of ln of x, we did integration by parts, and we had this answer down here. So I'm just going to go ahead and insert that into our problem down here. So what we get now is this is x times ln of x squared minus 2 times the integral of ln of x. The integral of ln of x, we just saw was x, ln of x minus x. And then we have that plus c. But we have to distribute this too. Alright? So if I distribute the 2, I end up with x times ln of x squared minus 2x ln of x plus 2x, and then all of that plus c. If we really wanted to, we can factor out the x because everything here has an x. So I can write this as x times ln of x squared minus 2 ln of x plus 2, and then all of that plus c. All right. Let's do one last one here. All right. So this is going to be example K. All right. So here we go. Example K. And it says the integral of x to the 7th times the square root of 5 plus 3x to the 4th dx. All right. So that's what we've got there. All right. So in here, we're going to start by rewriting this a little bit. All right. Now, as far as how to tell how to rewrite this, well, there's no real hint as how it's written that would tell me to do this besides experience. All right. So in here, it's basically just experience what I'm about to do. So you should be amazed at how much experience I've got with this. So now, what I'm going to start with is I'm going to let t be equal to x to the 4th. Therefore, dt would be 4x cubed dx. And I'm taking that from here, all right, just from the inside there. So when I do that, what does this do? Well, this integral, this x to the 7th, we didn't use for anything. The square root of 5 plus 3x to the 4th becomes 5 plus 3t. And you know what? I'm going to not write that as a square root. I'm going to write it as to the power of 1/2. And then that dx, well, that dx from here, we know it's dt over 4x cubed. So let's write that, dt over 4x cubed. And at that point, I'm going to reduce the x's, and I'm going to factor out that 1/4. Right, that 1/4 does not need to be inside the integral, so I have 1/4 integral of x to the 4th times 5 plus 3t to the 1/2 dt, right? The x to the 7th and x to the 3rd become x to the 4th. But now look at this. X to the 4th, that's just t. That's just our value of t. So what we can say here is this becomes 1/4 integral of t times 5 plus 3t to the 1/2 dt. All right. Now what we have is a product of two functions there, t and 5 plus 3t to the 1/2. Now, as far as which one should be u, well, this one's kind of difficult in the sense of all we've got is a bunch of algebraic stuff, right? So how do we decide what should be the u? Well, this one just essentially becomes trial and error as to what u should be. But I will tell you that in here, u should be t, and then dv would be the rest of this. So 5 plus 3t to the 1/2 dt. And then from here, du would be just dt. And then v, well, I'm going to skip the actual step of showing you fully how this gets integrated. But essentially, it's a u substitution, all right, to make this integral. And it'll be 5 plus 3t to the 3/2. All of this times 2 over 9. All right, that's correct. That should be a 9. All right. So now, at this point, we're going to say, well, this becomes UV. Well, don't forget about the 1/4 on the outside. 1/4 times UV. So I have, I'll write this as 2t times 5 plus 3t to the 3/2 over 9. That's our UV, minus integral of V, which was 2 times 5 plus 3t to the 3/2 over 9, times du, which is just dt. All right. So at that point, well, let's integrate that. That integral becomes, well, let's just copy this first. 2t times 5 plus 3t to the 3/2 over 9, minus, these two 9s are still sort of out here on the outside, so I write them out here, these two 9s, and then this part, when I integrate it, becomes 5 plus, well, hold on, let me make some space, 5 plus 3t to the 5/2, and over this times 2/5, and then over 3. All right. Now, as far as how I got these things, these two 9s are right there. These 2/5 are the reciprocal of 5/2. This 3 is this 3. All right. Now, that takes a lot of practice to be able to do it as quickly as I did. All right. You should be at this point still just doing the long version of these integrals. All right. Do the u substitution and see what happens. Okay. Now, the next thing we're going to do here is we're going to distribute. All right. Let's distribute that 1/4. All right. If I distribute that 1/4, well, I end up with the 2 and the 4 reduced. So I have t times 5 plus 3t to the 3/2, all of this over 9, minus, if I distribute this 1/4, the 1/4 and the 2's cancel each other out. So I have 9 times 5 is 45. 45 times 3 is 135. All right. And I just realized that I canceled too much stuff out in the first one. The 2 and 4 reduced to just be 2 on the bottom. 2 times 9 is not 9. It's 18. There we go. Sorry. Back to this stuff that we had over here. We have a 5 plus 3t to the 5/2 plus c. The next thing I'm going to do there is, well, the problem wasn't about t. All right. The problem was not about t. It was about x to the 4th, right? I started by making t be x to the 4th. So what I'm going to do here is I'm going to go ahead and plug that in there for t. So I'm going to get now x to the 4th times 5 plus 3t to the 3/2 over 18 minus 5 plus 3x to the 4th to the 5/2 over 135. All right. And then all of this plus c. So that would be our final answer there. And that is the end of 8.2, which again was just a bunch of integration by parts.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.